Thanks for the introduction. Thank the conference for inviting me for recognize this paper. So today I will talk about numerical strategy to solve multi-scale problems. Recently, when this Hilbert six problem it becomes very hot due to the breakthrough of Yue Dan and his colleague in Chicago. So I actually what I talk about is can be viewed discrete analog of the Hilbert six problem. So that's my subtitle. If you look at the physics, there's four fundamental scales, okay, from quantum mechanics at the bottom, which is valid, then molecular dynamics, kinetic theory, and hydrodynamics. Each of these equations has its own validity within a certain length scale and time scale. If you ignore if you ignore relativistic effect, then that's basically all you need to describe physics as these four important scales. In a lot of practical applications, there are a lot of problems where you have to solve multi-scale problems. For example, if you simulate the space shuttle reentry problem, then it goes through from rarefied gas area at a very high altitude to dense gas in the altitude where we live on. So if you look at the mean free path between the molecules, the distance between on our altitude, the mean free path, which is the average distance between two collisions of molecules, is about 10 to the minus 8 meters. But if you, for the space shuttle traveling in hundreds of kilometers, the mean free path can be order of meters. All right, so that's very rarefied gas. So the dynamics does not work in the high altitude. So there you have to solve, for example, multi-scale problem. And also in supersonic flight, when the flight travels with a usually with a Mach number bigger than 1.4, and if you simulate Navier-Stokes equation, you will find that the shock length becomes inaccurate if you compare it with, for example, simulation based on Boltzmann equations. And for example, if you want to model cracks, usually the crack away from the cracks, you can use continuum mechanics, right? Continuum relations. But around the crack, those continuum relations are not valid, not good. So you have to do molecular dynamic simulation. So therefore, you have to couple a molecular dynamic simulation with a continuum mechanics simulation. All right. And also in chemical reactions, where usually you have to do a lot of quantum dynamic simulations. So very viable numerical tool is to mix classical and quantum computation. So this is basically, this article is a review article published in Cambridge Press, University Press, Acta Numerica. After the publication, they made a beautiful poster. I really appreciate their professionalism because they made this complete. I did not provide any input. They read my article, they produce this, and either myself or my student can never produce such a beautiful professional poster. So basically, here my talk will involve all these scales from quantum, microscopic, mesoscopic to macroscopic. And mathematically, actually, you can derive this macroscopic equation from microscopic equations asymptotically. So here are three fundamental asymptotic from quantum mechanics. For example, is described by Schrödinger equation. All right. So if you take so-called semi-class limit by sending the Planck constant to zero, using the Wigner transform, you can derive Newton dynamics, classical mechanics. Then from classical mechanics, if you take the BBGKY hierarchy and take a Mikl limit, that limit is called Boltzmann limit. Then you can get the Boltzmann equation. That's the mesoscopic equation. Then from Boltzmann, if you take so-called fluid dynamic limit, you let the mean free path go to zero, you can find the fluid dynamics equations, right? So our work actually is sort of discrete analogs of this asymptotic transition. So basically, we want to build numerical schemes which kind of mimic this limit. And those schemes are very useful to compute the multi-scale problems. So I will get into those details. So basically, mathematically, you can always derive the macroscopic models from microscopic ones, all right? And so understanding these transitions from one scale to the other and also rigorously proving them has been a central topic in modern PDs and mathematical physics, which generate a lot of exciting works, including field metal works. And so that's exactly what this Hilbert's sixth problem was about. So Hilbert, for there's some physics here. So in the International Congress of Mathematicians in 1900, Hilbert announced 23 major math problems to be solved in the last century. So this is what we call the sixth problem. Essentially, it's about axiomatized physics. So basically, you want to rigorously justify these asymptotic transitions from one scale to the other. All right. And of course, these are not only important mathematically, they are also important. This transition for you to design and also analyze multi-scale computational methods. All right, so let me start with quantum mechanics. All right, so quantum mechanics simulation is viewed as so-called first principle calculation. There you have to solve n-body Schrodinger equations. So here I write the n-body Schrodinger equation where phi is a complex value of the wave function. H bar is so-called Planck constant. It's a very small number. And here x, y are coordinates, where x is coordinate of the nuclei, and y is coordinate of the electron. Right. So H is so-called Hamiltonian, which has basically two parts: kinetic energy and potential energy. So I separate this Hamiltonian into this is the kinetic energy for nuclei. X is nuclei, right? So all the other part that has to do with electrons, I loaded in He, which has the kinetic energy for the electrons. The rest are just potential Coulomb interaction between these particles. So this is Coulomb interaction between two electrons. That's Coulomb interaction between two nuclei, where the Z's are just the charge particles. That's the Coulomb interaction between nuclei and electrons. Okay, so that's the Hamiltonian. So first principle calculation means that you solve this equation, all right? And the difficulty of this is solving this equation is that the problem is just simply too big to put into your classical computer, all right? Well, ideally, if you are able to solve this equation, you can understand everything about our physical world, all right? For example, you can design all kinds of drugs. But that's impossible, according to Richard Feynman. This is an impossible task for classical computer. That's why we need a quantum computer, all right? Because here you have solved equations in hundreds of dimensions. For example, if you want to simulate the molecules carbon dioxide, it's 75 dimension Schrodinger equation. But our world is 3D. Solving three-dimensional Navier is already hard enough. Here we talk about 75 dimension. For benzene, it's 62 dimensions. So this problem is just cursive dimensionality, just simply impossible for classical computer. So that's why 40 years ago, Richard Feynman suggested we should develop a quantum computer to solve this equation. All right. Well, because this cursive dimensionality, so physicists have proposed a lot of different ideas to reduce dimension. So here I give two famous examples. One is Oppenheimer approximation. This movie was very popular last year. I mean, probably you saw the movie, but very few people probably know his works. The movie didn't mention that's his PhD thesis. This famous Chinese solid physicist called Huang Kun, who also did important work along this line. And then Ehrenfrost dynamics is another way to separate computation from electrons from nuclei. Another more possible class simulation is taking so-called field approximation. So instead of n-body Schrodinger equation, where you have solved PDE of 3n dimension, you reduce it, make some approximation, maybe become a one-dimensional PDE. Okay? For example, just three-dimensional equations. So here are a few examples where you can take a Hartree-Fock theory, density function theory. That won Nobel Prize in chemistry in 1998. So these are so-called one-body approximation, mean field approximation. Now let's come to classical mechanics. So classical mechanics is the equation that everybody knows since high school. F equals ma, Newton's second law. All right. So if you consider n particles, then actually this is the equation that describes the movement of particles, where the Q, I are just the momentum of ice particle, all right? The velocity and P is the momentum, sorry. P is the momentum, Q is velocity. With dot means time derivative. The Mi is the mass. So the second, so this is the definition, all right? The velocity derivative is the position. A position derivative is velocity. And then you have equals ma. So this is F. So Pi is just ma, where P is the mass times velocity, okay, time derivative. So usually the force is a gradient of negative gradient of potential, release potential. So this is actually a Hamiltonian system. It's ODE. But the problem is that these particle numbers can be very large. Here are just some examples. All right. So for example, if you talk about cosmology or astrophysics, you're talking about particle 10 to 20. Also in plasmas. Also, the particle method are often used as a numerical method, so the Lagrangian simulation, where the largest scale particle simulation can reach 10 to 9 into 10 to 12. All right. And there's many other applications where the n is just too, very big. So that's the problem with Newton simulations. N is too large. And then so the mesoscope scale is kinetic theory. That's where the scale where the statistical physics is developed. So here you do not trace each particle's trajectory velocity. You consider the probability density function f, which depends on time t, space x, and the velocity, right? And it's solved this so-called the Boltzmann equation, where it has two parts. The left part is just the convection. So particles with velocity v will just transport with velocity v. This is just linear transport. The right-hand side describes the interaction in particles. Here, the interactions are basically collisions. Particles just collide and bounce back. All right, it's elastic collision. So the collision operator is complicated. So it's quadratic nonlinear. You have two particle interaction. All right, so it's quadratic. And this is collision kernel, which has to do with what kind of molecules you use. And it's d-dimensional integration in space. And this is you have a integration in the unit sphere, d-dimensional unit sphere. And here the particles collide according to it's an elastic collision, so it conserves mass, momentum, energy. All right. And actually, Maxwell actually first derived this equation, but it's called Boltzmann because people forgot Maxwell. Well, he had nothing from the equations anyway. It's because he discovered this fundamental identity. In the part, it's called entropy H0. It's called entropy condition, where F log F is the so-called entropy. So finally, at the hydrodynamic level, so the fundamental equation, for example, if you describe fluid dynamics, it's Euler and the Navier-Stokes equation, which are essentially the fluid equation has two parts. One is conservation law, right? You have conservation mass, momentum, energy, and it's nonlinear, all right? So here you see those nonlinear terms. So if the right hand side is zero, it's called ideal gas. That's the Euler equation. And of course, this equation is not closed because the rho density, velocity, momentum, and the E is energy. But you have this other variable like pressure. So you have to close the equation, you have to write pressure as a function of density, momentum, energy, right? So these are called the equation of state. And now, so basically, a fluid equation is just two parts: conservation laws plus equation of state or considerable relation. All right, you need considerable relation. So that's the fluid dynamic equations. All right. Of course, so these are all equations that are valid at its own scale, and if they are all correct, then there must be some connections between these different equations. All right. So that's what where we are very interested. How do we connect these equations? All right. What are the connections? And then if you found the connection, you will try to justify rigorous mathematically that have generated some of the most exciting mathematical results in PDEs and mathematical physics. So, all right. So what I just described is exactly what the Hilbert sixth problem is about, right? So he basically he said, well, here are all these connections between all the physical laws at different scales. How do we justify them mathematically? All right. So in particular, for example, if you start with microscopic models, Schrödinger equations or Newton equations, they are actually time irreversible because those are Hamiltonian systems. You can go backwards in time. But at the kinetic equation of hydrodynamics, we know there's something called entropy. which makes things time irreversible. So how come a time reversible process, okay, as you go along, you increase the scale, becomes time irreversible. And also, how come when Schrodinger equation and the Newton equation have a big degree of freedom, right? But if you go to fluid dynamic equations, just 5 equations, these 3 is 5 equations. And how come one can replace a very complex system with many degree freedom by something that involves a few degree freedom? So these are all very interesting questions. Actually, Hilbert himself was trying to try to connect kinetic equations with hydrodynamic equations. He actually made some effort on this, although he didn't fully solve this problem. So now let me give you, so that's a rough idea, right? I mean, about these 4 fundamental equations. So next I will talk about their mathematical connections. All right. So let me start with quantum mechanics. So this is Schrodinger equation. I just represent the general potential by V. Okay. So it's a linear PD. Okay. The mathematics is very simple. So here I take a non-dimensionalized equation. So I get rid of this H bar. So I replace by a dimensionless number epsilon. That's dimensionless Schrodinger Planck constant. If something is a small parameter, right? So a good mathematical tool to connect quantum mechanics with classical mechanics is take so-called Wigner transform. So Wigner, here's the Wigner transform, which is essentially it's a Fourier transform, but on this quantity it's a quadratic quantity. U and U bar means complex conjugate. All right, but at different position here. So this U times U bar actually is density matrix. All right. So here you actually take Fourier transform on this eta variable. All right, you get psi. So then you get a function called a Wigner function that not only depends on time and x, but also depends on this new psi variable. So it's defined in phase space. And then you can write, it's very easy to derive. Suppose you solve Schrodinger equation, then W solve this so-called Wigner equation. Well, this free transport part, the Laplacian, I can give you this linear transport, right? So it's transported with velocity psi. And then you have a scattering term comes from this potential term, which is actually a pseudo differential operator. Where delta V is given here. So this equation is sort of an equivalent form of Schrodinger equation, or Wigner equation. Now, this term, if we assume epsilon small, if I take a Taylor expansion, all right, on this term, then you can see Taylor expansion around x. Then you see the leading order they will cancel because you have minus term. The next order will not cancel, you get gradient of V. And gradient V dot with epsilon over 2 times y, minus that. So you get the epsilon, you cancel this epsilon. So if you expand to the next order, and you find that actually you get this term. And then you ignore, let's set the epsilon to 0 formally, actually get this equation that's classical Liouville equation. All right. So this is Liouville equation in the classical mechanics, which is the basically equivalent to Newton's equation. Now, well, this is a linear transport equation, which can also be solved by method characteristics. So if you define the characteristics of the linear transport, dx dt equals psi, and d psi dt equals this minus v gradient. And this is exactly Newton's equation. Okay, dx dt is velocity. Assume the mass is 1. Velocity times derivative is acceleration. Give you the force. Force is negative potential gradient. So you exactly get the Newton's equation. By sending epsilon 0 on Schrodinger, epsilon is sort of a dimensionless Planck constant. Essentially, send Planck constant 0, you get the Newton's equation. So essentially, well, the quantum mechanics is about waves. Okay? And the waves looks like this, while the classical particles are just basically a wave packet. It's a wave packet. So waves are highly oscillatory. Schrodinger equation is a wave that oscillates with this length scale, which is all the epsilon. Right? So now you send epsilon 0, all this high frequency wave becomes a wave packet, and each wave packet is a particle. There has been a very important mathematical works by, for example, fields medalist Lyons, Markovich, and so these people in the 90s. Okay, now from quantum mechanics we derive Newton's equation. Now let me start with Newton's equation. All right. So I can see the n-body Newton's equation have n particles. So the first line again is definition, df dt is velocity. Second line is f equals ma. All right. So this is a, okay, velocity time derivative. And here the interactions you have a, okay. So the interactions are particle between the particles. So these are the forcing term is minus the potential. So these are binary interactions. Each particle will interact with all the other particles. So now I denote a big vector. So I put this position and the velocity to a big vector. All right, all these positions and velocity vectors in a big vector, and I choose property measure. Okay, W, which depends on the Z, which is a vector of space and velocity. And then actually for this probability measure actually solves the Liouville equation. Where this Newton's equation is basically just by characteristic of the Newton's equation. All right, so this you got the Liouville equation. All right, so this is convection term due to velocity, and this is forcing term. All right. Now I try to take limit. I set n to infinity. Okay, I assume that the particle number goes to infinity. To do that, of course, because my W depends on m particles. So if you send n to infinity, this guy has infinite dimension. And now I have to introduce so-called marginal distribution. So now I'm going to have, before W depends on n, two n variables. Now I'm going to integrate part of the variable. For example, integrate from zj to zn. That's called the nth particle margin, right? Here I have to make some assumptions. Okay. The first assumption is that all particles are exactly identical, which means if I interchange the position, all these values z's, W remain unchanged. Okay. First, all particles are equally treated. They are completely identical. Second assumption is very important, so-called molecular chaos. So essentially, I can, this is two-body distribution. I can factorize into one-body distribution because these particles are independent. So if this is a probability distribution, they are independent. Right? So this is called a molecular chaos. They're complete chaos. Okay. They are completely in chaos. That's why we can factorize the distributions. And some other assumption we have to make to derive Boltzmann equation. First is epsilon, which is the so-called mean free path. That's average distance between two collisions. Okay. We set to that to be 0 to 0, so all the particles are kind of packed to each other. And the n of course goes to infinity. But as you can see, if you have this room, you have m particles. If you let the n go to infinity, even go to 0, if epsilon has to go to 0, otherwise you cannot fill all these particles in this room. Right? But they have to be set to 0 with certain ratio. So n times sigma squared, this should be capital N, has to go to be constant. So this is called a ratified gas. Usually n scales like this one cube, but here we assume n scale like this one squared. So this is a ratified gas. Fixed at constant. So this is called a Boltzmann-Grad limit. And then actually can sort of derive dynamics for F1, one body F, which is exactly the Boltzmann equation. Okay, so that's how you get Boltzmann equation for Newton equation. However, the proof of this is very challenging. All right, the first milestone is the long result in 1974, where he rigorously justified this limit within a very short time. It's called one fractional mean free path, which means you even particle even didn't complete one collision. Okay, it's very short time. It's valid. Well, later this French school has improved the result. Right? But it's really recently there's a big breakthrough involved this. Well, that's your colleague Xiao Ma in Michigan, USM. So they announced the result where they can prove this validity all time for as long as solution for Boltzmann is valid. That's this landmark result, in my opinion. So this book generated a lot of publicity in the last half months. All right. So finally, how to derive from Boltzmann to Froude equation? So here I start with Boltzmann, where epsilon is a small parameter, it's mean free path, but I not dimensionalize it. So it's called the Newton's number. All right. So well, F depends on x and v. So if you integrate over v, so for take moments. And this zeroth moment is give you so-called the density. The first moment you multiply V, F multiplied by the integrate called the momentum. Right? So this density times velocity is the moment. For a second moment, actually, you can define so-called temperature. So these are so-called moments. And then essentially just multiply this equation by V to some integer power and integrate. So-called taking the moments. If you directly integrate, multiply V to the power 0, you actually get this first equation. All right, so-called conservation mass. And if you multiply by V and integrate, you get this conservation momentum. And multiply by 1/2 V squared, you get conservation total energy. All right. And total energy has two parts: kinetic energy plus internal energy. But here, of course, these unknowns you have in 3D you have 5 unknowns, right? This N and E are scalar, where E is 3D, so 5. You have 5 moments. But here there's some other symbols here. P is the stress tensor, Q is the heat flux. And these equations are not actually not closed because every time you multiply V to some power, there's always one extra power. Okay, so here we have 5 moments. Here you involve moments that involves higher moments. So this equation cannot be, it's not closed. So how do we close the equation? Now we send epsilon to 0. So epsilon is a Lewis number, so it's mean free path. Essentially, it's a mean free path. If you set a mean free path to 0, it means all the particles get very dense. I mean, they are very dense. They're very close to each other. If you look at this picture here, it's equal, you will view this as a rarefied gas. But here, when particles are very close to each other, mean free path is small. It's like more like fluids. So if you take epsilon 0, the lead order from the leading order asymptotics, you see that this is order 1, right? If this guy goes to 0, epsilon goes to 0, this guy has to go to 0. Q has to go to 0. When Q is 0, actually, you can uniquely determine F, which is so-called local max weighting. Okay. Then you can write F when Q equals 0, F can be solved as a function of the N mass, temperature, and velocity. Okay. Now with this particular F, then actually can define this P and Q in terms of these variables. Then the equation is closed. Okay. And that equation is nothing but exactly the Euler equation, compressible Euler equation. Okay. And well, then you say, well, epsilon in red is not, it's small, but not really 0. Okay, so it's not really 0. So if you take a next order expansion, it's called the Navier-Stokes expansion. The Navier-Stokes Chapman-Engelsk expansion. Then you actually next order, which give you exactly the Navier-Stokes equation. So the Navier-Stokes equation is basically Euler equation plus viscosity and heat conductivity. So you can derive the next order, which give you exactly the Navier-Stokes equation. So therefore, fluid dynamics are exactly the asymptotic truncation from Boltzmann. All right. So it's very much like when you have very few particles. These are particle systems, but when they are bumper to bumper, and you have tropic flow, it's flow. Okay, so it's called flow. So that's the asymptotic transitions from a particle system, ratified gas to dense gas, which become fluids. And again, to prove this is very difficult. Okay, incompressible. The program of proving this fluid dynamics from Boltzmann started in the early 90s. This French school, Claude Bardot, France Gauss, Dave Lemon was my and Peter's advisor. So they start this when I was in Arizona. We're both PhD students in Arizona. And this finally for incompressible limit was completely solved by Francois Gauss and Laurie Saint-Raymond. Saint-Raymond was Francois' PhD student. However, the compressible limit is still open. It's very difficult. The reason is that if you have compressible flow, you may develop shocks. So the expert, Qi Wangshu, who is expert on how to compute shocks. We have shocks, and the proof of this becomes very hard. All right, so let me summarize what we have talked about. Well, first, all these macroscopic equations are simply asymptotic limits of these microscopic equations. You can see the mathematical bridge, which connect all these equations in these 4 fundamental scales. They're all mathematically connected. Okay. And well, the microscopic equations are all linear equations. Okay. For example, quantum equation, Schrodinger equation is linear. Well, Newton's equation is not linear, but Lewis equation is linear. If you put it in the phase space, it's linear. So this microscopic linear, which is mathematically easier, But computation is a challenge because the number of degree freedom is too large. You have close to dimensionality. And these macroscopic equations, be they kinetic or fluid equations, they are nonlinear. So mathematically, they are challenged. Okay? Mathematical justification is very challenged. And they're also time reversible. Okay? The classical, the microscopic models are time reversible, but these macroscopic are time irreversible. So the mathematical theory for macroscopic equations are very hard. Okay, these are nonlinear PDEs, very difficult. If you have big result, you can feel them. But the numerical computation is harder at the microscopic level. Not because the equations are easier, but the degree of freedom is too large. You have too close to dimensionality. All right. So basically, now I come back to this poster. Essentially, I explain how the mathematical transition between one scale to the other, right? They are all connected by this asymptotic analysis. So I will show you a numerical strategy which sort of can be really viewed as discrete analog of all these asymptotic transitions. Okay. So that's why I call this discrete version of Hilbert 6 problem. So here, this picture actually shows for the basic idea what we call asymptotic-preserving scheme. So suppose you start with a physical model, which depends on some small scale epsilon. Okay, a small scale epsilon. And if you take epsilon to 0, you get some macroscopic equation. For example, if this is Boltzmann, when the Nernst number goes to 0, you get a full equation. Now, if I discretize this system, then I have a numerical parameter delta, which may be time step and the mesh size delta x, right? And of course, this numerical method, if the numerical parameter go to 0, it should convert. The numerical method should convert. So for fixed epsilon, when delta go to 0, it should converge to this equation. Okay, that's numerical convergence. However, if you take a truncation error analysis, I mean, this epsilon usually appears, you have 1 over epsilon. Okay, you have 1 over epsilon. So if you take truncation error, you find the truncation error will be divided by epsilon. Okay, which means that your consistency, for consistency, your delta has to be smaller than epsilon. Which means you have to resolve the small scale. If you compute some physical problem with small scale, your mesh size has to be small enough to resolve the small scale. But the asymptotic preserving means actually, now I showed you how to derive from microscopic model to macroscopic model or asymptotically. Now if I start with discrete microscopic model, I view this as discrete microscopic model. Again, I take the same limit. I set even 0, but I keep delta fixed. Okay, I keep the numerical parameter time step method fixed. Okay, I take a discrete, that's discrete analog of this asymptotic limit. Now I'm going to end up a system which no longer depends on epsilon, but still depends on this delta. Okay, and if that discrete system happens to be a good approximation of this equation, I call it asymptotic preserving. Which means basically I have discrete analog of this asymptotic limit. Okay, so here from is Boltzmann to Euler. So here I have discrete Boltzmann. When I send even 0, I get discrete Euler. Some nice scheme for Euler. Then I call it asymptotic preserving. In other words, and this limit I can set delta to 0 first and then take even to 0. And it commutes with a limit that I send even to 0 first and delta to 0 second. So this diagram commutes. That is called AP. What's good about this method? They usually have multiscale method. You have maybe a microscopic scale kinetic equation fluid. You have to couple these two equations by some interface. All right. So one side is solve kinetic equation, for example, space shuttle, where high altitude is solve Boltzmann, low altitude is solve Navier-Stokes. But you have to couple these nonlinear PDEs, which is very difficult because you have to put a boundary condition, you don't know where to put it, and you have to provide boundary conditions to connect these two equations. Right? And the boundary condition is very difficult because from microscopic to macroscopic is easy, you take average moments. But the other way is difficult. If you take a macroscopic to microscopic, like a macroscopic is average. The macroscopic is average, and from average to point-wise value, that's difficult. So connect these two scales is difficult. But this method does not need to connect. It just solve one equation. Okay, and this equation, if you resolve numeric mesh size is small enough to resolve epsilon, you are solving the microscopic equation. If you don't resolve, effectively you are solving a macroscopic equation. It's very much like if I want to eat shrimp. I have a fishing mesh. The mesh size has to be smaller than the size of the shrimp for me to catch the shrimp. If I have a coarse mesh that's bigger than shrimp, the shrimp will drop. But if I can get the lobster, I'm going to be very happy. Okay, I still have good seafood. So you have a coarse mesh. You can capture the macroscopic behavior. You miss the microscopic details, but can capture the average macroscopic scale. You're still happy. So that's what this scheme can do for you. All right. So basically, that's what the way you can do it. When small physical scales are resolved numerically, if your mesh size is small enough, you are computing the microscopic equations. But otherwise, if the mesh size is too coarse, then you hope you can capture the macroscopic behavior. That will be enough. Okay. And the numeric scheme do this automatically. Okay. You don't have the artificial switch between one solver and another solver. You have Boltzmann solver, network solver. You don't have to artificially connect the solver. Just one solver, which take care of both regimes. All right. So why this work? Okay, why this work? Well, I do a very formal analysis. If you, but this I showed you, right? I mean, the distance between microscopic model and macroscopic one says all the epsilon from this asymptotic expansion. And if you do classical numerical, suppose I solve a problem with dependent on epsilon. If I solve this problem with delta, then usually, I mean, because this delta appears, you have 1 over delta, right? So that truncation error will be some numerical consistent error. If you have R's order, delta to power R, divided by epsilon to some power. All right, so that's classical numerical analysis. Of course, it's not good, but epsilon is very small. Your delta has to be small, depending on epsilon. On the other hand, if the scheme is asymptotic-preserving, then I can do the same asymptotic analysis from discrete, say Boltzmann to discrete Euler. That means I can get this error estimate, where this error between this and this is all the epsilon, but uniform in delta. Okay, that's what AP means. Then of course, this is good scheme to that, and distance between this and that is all the delta, depending on all the delta. Right? If this is as AP, this is a good scheme for that. You have error, which is all the delta. So now I have two error analysis. One is the direct, like by Lux equivalence theorem, direct computation, which is very good when epsilon is large, but bad when epsilon is small. So that's this curve. Okay, that's this curve. It's very good when epsilon is large, but bad when epsilon is small. And now I can have another error analysis, which just stupid triangle. You call it. I add all these three errors. Okay. So then that's then you get this error. Okay. So here is all the epsilon, all the epsilon, all the delta. So you get this error. And this error, of course, is very good when epsilon is small, but bad when epsilon large. So that's this curve. Both error analyses are valid. Okay. So which means I can take the minimum of these two. And when the worst case scenario is when these two curves intersect. That's here. And they intersect when epsilon is essentially this order of delta. Now if I plug this epsilon equal delta to what to here, any one of this actually I get is a uniform error analysis. Now I can see that if this scheme is AP, the method is uniform epsilon, which means I take delta. I only have to take delta according to my accuracy requirement. Okay, I don't care what epsilon is. All right, so we have been playing this game in the last 2 decades. We played all these scales from quantum to quantum to Liouville to kinetic and kinetic Boltzmann. So here, actually, what we found. All right, first for quantum to classical, you have discrete Schrodinger. You hope when H bar goes to zero, you get discrete Euler, get discrete Newton equation. And this is very challenging actually, and it's what the best we can do is that for time we can do it. Okay, we can design scheme where delta t can be independent of epsilon if you only want to compute observables. But for space, the best you can do is actually delta x has to be square root of epsilon. Okay, so that's the method known as a Gaussian wave packet method. Like Xu Yang here from Santa Barbara, he's expert on these kind of things. And this part I struggled for a very long time until last few years. Finally, I had some good idea from how to get m body from m body to Liouville equation, Newton equation, how to get Boltzmann kinetic equation. Oh, this one I'll talk about. We have this random batch method which sort of partly solve this problem. And then from discrete Boltzmann to discrete has been the most successful program, right? Essentially, we are able to design scheme which works for both kinetic fluid equation, for both delta x and delta t and delta v, for all the numeric parameters. So this, I also will talk a little bit about this. Okay. So let me give you examples. Okay. Suppose I want to solve Boltzmann equation. Okay. So here epsilon is very small, and collision is very concave. Of course, the first challenge is that this problem is a numerical stiff, because when epsilon is small, you need small time step if you have an explicit scheme. So time step has very small, so it's very slow, it takes a long time. But it's more than that. You say, well, that's easy, I do implicit scheme. Okay? Then delta t can be anything, much larger than epsilon. However, here I talk about if you have implicit scheme, then you have to invert this crazy operator. It's 5 dimensions, non-linear, it's non-local. So inverting this big matrix is daunting. So it's very hard. But what we did actually is that we take a penalty. Okay? So we penalize this Boltzmann collision operator Q divided by epsilon by a simpler operator. It's called a BGK operator, right? So the BGK operator essentially M is this local Maxwellian. So it's the local Maxwellian minus F. I penalize, subtract this term and add this term. So if I take a suitable beta some constant, if I take a suitable constant, then it turns out there's some cancellation effect between these two. Because this can be used sort of like Taylor expansion of leading or Taylor expansion of this. So cancel out the most stiff part. Okay, so this becomes, compared to that one, is less stiff. And this one is the stiff part, but it involves simpler operator. And now I can, this part I can take implicit, and this part I take explicit. Okay. So that's will be numerical stable. However, here this M, remember this Maxwellian, which still depends on these moments. So it's still non-linear, highly non-linear, non-local. And this is something beautiful about Boltzmann equation. So here I take this term to be implicit, right? This is explicit. This IMAX, so IMAX. Now here I show you, although it looks implicit, but it can be solved explicitly. Okay, so it can be solved explicitly. The reason is because if I take moments, remember the Boltzmann I can take moments. Then because of the conservation laws, the right-hand side all vanish because the collisions are conserve mass moment and energy. So if you take first time moments, okay, the right-hand side vanishes, which means I can update f, the moments of f at the next time level. And once you have the moments of f, that will define your m. The m is defined. You got m. Now the rest is linear. Okay, the remaining top becomes linear. So I can define the implicit scheme. I can solve the implicit scheme explicitly. So essentially, it's explicit solve. Then I can becomes explicit. Well, now we have just the AP scheme. To prove the AP scheme, you have to show, well, when if goes 0, f becomes Maxwellian. This actually we can show you asymptotically. We can show you, so it's AP. So that's how we solve Boltzmann equation. And here numeric test shows you I can take epsilon a very small 10 to the minus 8, where mesh size is like 10 to the minus 2. It's much bigger than me. I can compute this like shock waves. Good. Okay, the next I will talk about how we solve particle system. Okay, some method I introduced with Lei Li and Jianguo Liu, who is at Duke. So here it's essentially Newton's equation. All right. So we assume a particle system. This x is position particles. This external potential, and here you have interactions between potentials. Okay, and you have maybe some noise from the motion term. So the difficult of this is actually because it's summation. All right, you have to add many terms. So each particle has to interact with all the other particles. So this all the n summation, and each particle you have to add n terms, and you have n particles. So it's all the n squared computation. All right, so it's quadratic computation. Quadratic computation is always hard. Remember last centuries, there are like 10 top algorithms. 2 of them are exactly handle all n squared. One is fast Fourier transform. Everybody knows fast Fourier. The other one is fast multiple method by Greengard and Lockley. So these are 2 top 10 algorithms of last century, all developed to handle this odd n squared. Well, also then you say, well, the particle you can take also take BBGKY, take a mean field limit if it defines over the empirical measure. You put the direct mass on each particle, and then you can prove and ascend n to infinity. You actually get Fock-Planck equation. All right, and this external force becomes drift term. This interaction term becomes it's a convolution of this kernel K with the density diffusion. Brownian motion, of course, becomes diffusion term. So that's the mean field limit. This is like from Newton to Boltzmann. All right, mean field limit. And now we introduce this random batch method, which is embarrassingly simple. Works beautifully. So idea is very simple. All right. So remember, we have these M particles here. Everybody has to interact with all the other particles. Now at each time step, I choose a small time step tau, some time step. At each time step, I randomly regroup all the particles. So suppose here we have 100 people. I group into small groups randomly, okay, into small groups. Each group has M particles, P particles. The key is P has much smaller than N. P can be as small as 2. When we have 100 by 100 interaction, I group into 50 groups, each with two particles, 2 people. Now at each time step, each particle only interact within the group. I forgot about all the particles. I only interact with the particle in the same group, small group. Okay, which means I replaced originally all the N summation to be all the P summation. P can be very small, can be even small as 2. Now this term becomes all the 1, which means my algorithm all the N, right? Something very simple. I hope it's something program you can finish in half hour. I'm sure you can write this program in half an hour. Very simple algorithm. Okay, the cost clearly is all the N. Well, you have to do this random shuffling. It's like when we play mahjong games. At the end of the game, you have to reshuffle, then reorder into four groups, right? It's the same story. You have to reshuffle. This shuffling algorithm is all the N. Okay? In the MATLAB, we just use something called random permutation. Okay, that's all the N algorithm. So overall, it's all the N algorithm. But of course, you can say, well, you are being lazy, right? You're not finishing the job. You're cheating. At each step, you only interact with small group. How about the rest? It looks like intuitively it takes n times longer to finish your work. If each time I interact with one person, 100%, it takes 150 times longer to finish. Then you're not saving. But here the key is that we can prove, okay, the algorithm works independent of the group. Okay, so essentially we have error estimate where there's some conditions which I ignore. So this is the exact solution. This is a random batch solution. You take the L1 or distance where you expect the value because it's a random, right? You can also take Watson distance, Watson 2 distance, which is the equivalent error. So essentially what we can prove that the Watson 2 distance is bounded by the square root of tau. Tau is like time step, okay? So why square root? Essentially what we have is a Monte Carlo method in time. Okay, we know Monte Carlo method is helps all the, if you have n samples to Monte Carlo, the area is 1 over square root of n. So here we have Monte Carlo in time. So that's why it's square root in time. But that's not very important. What's important is this constant c. We can prove the c actually is independent. Okay? So that means if I want error to be, say, smaller than epsilon, I just take time step to be 1 over epsilon squared. I don't care about n. N can be as big, 1 zillion, whatever, as big as you want. Okay? I can take time step independent of n. So I'm cheating, but it works. So sometimes cheating works. This is actually due to the law of large numbers. The law of large numbers. And essentially, I mean, well, the idea is to prove you have to assume some regularity in the potential, but in applications, we tried all different applications, including singular kernel. Okay, include singular kernel. Whoops. And what about AP? Actually, if you take n to infinity limit, you actually get this Fock-Planck equation. The mean field limit is Fock-Planck equation. So this method not only is a good method to solve a particle system, it also can be viewed as a particle method to solve the mean field equation, Fock-Planck equation. The error actually, the random batch error is like square root of tau. The mean field error is 1 over square root of n. All right. So if I view this as a numerical particle method to solve the mean-field kinetic equation, and this is my air. Okay, square root of tau plus 1 over square root of n. So it means that this method captures both regime, the particles, and also the mean-field limit. In that sense, it's so-called asymptotic-preserving for n. And so essentially, some of my colleagues joined this effort. Okay, we are solving real molecular dynamics. So we have real molecular dynamics, then the F becomes very concave, all right? So you have a force due to bonds, angles, torsions. You have a Taylor-Jones potential, right, which can be singular. And the most difficult part is this Coulomb potential, Coulomb interaction. So Coulomb interaction is 1 over the distance between two particles. Rij is the distance between particle I, particle j, electrons here. This Qi is like a charge, all right? So this is clearly all the n squared. Of course, molecular dynamics has a lot of applications, from AI drug design to material design. Okay? It has a lot of important applications. So our idea is actually built on this so-called classical Ewald method. The Ewald method, basically, you write 1 over r. The Ewald is beautiful idea, right? But polar interaction is like this 1 over r. It's called long-range interaction because it decays very slowly. The 1 over r decay. Okay. To truncate r, the r has to be very large. So the idea is you take air function r divided by r. Put in some constant plus 1 minus air. It's called Ewald. This is a simple algebra. And it turns out that this part is actually smooth when r goes to 0. And this part decays exponentially in r. So this part can be viewed as a long range, a short range, because decays very fast. Truncate when r is large, not very large, you can truncate. But this one is r is a removable singularity when r equals 0. So this is because smooth, I can take a Fourier transform. I put in the Fourier space because it's smooth. And because it's a smooth function, the Fourier mode decays. That's why you have e to the minus k squared. Okay. And now this short range interaction, I just take some as it is, because short range interaction, the summation is all the 1. While for this smooth part, I take exponential term. Now you have many Fourier modes. Now I use this random batch. I just randomly select a few Fourier modes, k, do the summation. Okay, that's random batch. With that, the cost is of computing summation is all the 1. Another thing is that you have this e to the minus k squared. That's Gaussian distribution. So we can pre-sample k from Gaussian distribution. That's like important sampling. So I do important sampling according to Gaussian. I pre-sampled Gaussian and saved in the library. I just draw randomly a few k's each time I do the summation. Okay, so I combine random summation with important sampling, which allow us to reduce the variance, because Monte Carlo can be very noisy. But if you use important sampling, the noise is very small. That's the idea. All right, Hongner actually is biophysicist. He also tried some realistic problem. He used like 20,000 CPUs in SJDU, and he find incredible efficiency. It's highly parallel. You mean all these molecular dynamics, cutting state-of-art molecular dynamics like PBPM and PME. PPM is P particle measurement. They all use FFT. We know FFT is not parallel. It's not scalable because it's non-local in term summation. But this matters because it's a random batch. When you have a parallel process, the saving you have for each single CPU is completely overwhelmed by the message passing cost between the CPUs. You have to pass all the data between the CPUs. That takes more effort than the saving you get for a single CPU. But when you do random batch, each time only involve message passing over very few CPUs. Okay? I do not have to do message passing of all CPUs. I just each time step, just message passing among a few CPUs. So that significantly reduces the cost of message passing, which shows that it's highly parallel. So we have parallel efficiency, we have 10,000 CPUs. Parallel is almost 100%. If you do the PPPM, it's like 20%. It's highly parallel. And if you compute from femtosecond to nanosecond, that's 1 million time steps. You have a nice agreement with PPM. Here we take only each. So this is a particle is 10 to the 7, 10 to 6. But P, each batch has like 50 particles. Okay? Instead of 1 million, we only each mini batch has 50 particles. And then he also showed all agreement with all kind of test forms. And even this hydrodynamic kinetic potential energy, we see a very nice agreement. And then we also extend to other, well, for molecular dynamics, there are many other systems, MPT, ME, all these systems, ensembles. We can extend to those more realistic molecular dynamics. And very recently, actually, for the first time, well, we are not only use the random batch for long range, we also use random batch for short range. And we are able, the first time in the world, we are able to simulate with one GPU 10 to the 7 particles, 10 million particles. Before the record is 10 to 1 million, 10 to 6, but now we can do 10 to 7. With one GPU, which means on your desktop, in your office, you can do particle dimension with 10 to 7 particles. Okay? So we even combine with the GPU from 中科时光. Now we have desktop with this software built in. So you just have this by the desktop, you can do on your desk. You can do more dynamics with 10 to 7 particles. Well, actually, in Chongqing, we have a Chongqing AI Institute where, I mean, we have this software now, which is open source. If you're interested in using this software, you can use this. That's really state of the art. We also combine with this 中科曙光 some hardware, G1 GPU. So this now you can do desktop particle dynamic simulation with 10 million particles if you need to do this kind of scientific research. Why this is very exciting? I mean, you know this in AI. I mean, last year this year last year, sorry. This Nobel Prize in Chemistry gave to the AlphaFold, right? What AlphaFold does is give a sequence. You can predict very accurately the structure of proteins. Okay, that's the work of AlphaFold. And AlphaFold actually changed everything. Okay, now you can design. It's very important for drug design. So actually, this household name Yan Ning. At that time, he was Princeton. Now he came back to Shenzhen. So AlphaFold first came, and she said, "Well, AlphaFold of course is very important, but compared to what AlphaFold, he hoped the AI can help more molecular dynamic simulation. So for structural biology, this field is in urgent need progress." There's also another important work by Wei Yi and his group, where they use AI to learn. You remember if it solve F equals MA, usually the F is difficult to get. But they use AI combined with dense function theory to predict F for certain materials. All right, so you can use AI to help predict F, but once you have F, you have to solve F equals MA. So that's where our work fits. So it's very nice complement to what Wei Yi and his group did. So this area, of course, with AI drug design, material design, all of a sudden become very, very exciting. So this is actually the survey articles of my talk, which got the prize yesterday, published in Acta Numerica. So if you're interested, you can read these articles. So that's all I want to talk about. Thank you very much.
Any questions?
Yeah, Peter.
So very nice talk, and it's okay if I ask something about the beginning part of the talk.
Sure.
So you know, what's the usual justification? I mean, that people make, you know, for the molecular chaos assumption, because you said that this is the same as assuming independence of the particles.
Yes.
On the other hand, you right away, I don't mean you, but one derives right away a Boltzmann equation that has a collision term, and the particles are talking to each other through the collision term.
Yes.
And actually, when you go to the fluid dynamics, the mean free path goes to 0, and now you have a 1 over epsilon in front of that term that's supposed to not be there.
Yeah.
What's the usual argument?
Well, they, of course, molecular chaos simply is particle independent, right? Dense distribution are independent, but they do collide in a way. But here they collide in a way, they interact in a way that they are treated equally. Everybody is equal. Okay. They're completely identical. The distribution is independent, but they do collide. This collision gives you the Boltzmann collision term. Yeah. So there's no contradiction between molecular chaos and the collision. Validity molecular chaos, that's what Dan's work proved, like I mean, they are able to prove molecules. That which actually, in my opinion, I think this work is significant of Deng Yue is because it sort of just prove mathematically defined very clearly what entropy is. Because with molecular chaos, you get this concept of entropy, which looks mysterious. From something time reversible, also offset from delta equaling offset get Boltzmann, which is time irreversible. I think Deng Yue's contribution, which deserve more, is more important than some people thought. I think it deserves. I think it deserves a very high big price. Anyway, so they really give a very mathematical definition what entropy is, how entropy arises is from molecular chaos. I think that's important in their work, which I don't think was very clear mathematically before.
Okay, thank you.
Yeah, sure.
Any other?
Pardon? You mean for our molecular dynamic simulation? Now we can do molecular dynamization, 10 million particles. This joke in Anton, you can finish your job before launch. So essentially, well, what we can do now with one GPU, we can simulate 10 to 7 molecular dynamics in just a few hours, from femtosecond to nanosecond, which means 1 million time steps in a few hours. Pardon? Not for, well, yeah, well, that's the work with, if you have a smooth potential, then we have air estimate. Not for Coulomb interaction, that's hard, because it's very single. So for this random batch, I did with Django Liu. So we have air mass. We have this random batch mass, which means each time you have n particles. We randomly group of particles. Each particle only interact within a small group. All right. So the P is small group size, where tau is time step. So essentially, it's all the area is square root of tau. It's like a Monte Carlo in time. It's a Monte Carlo area. But here we have the assumed potential smooth. For Coulomb potential, we are not able to prove here, but Coulomb singular is very, very difficult. But we do have this molecular dynamic algorithm which handles singularity very well by this Ewald split.
Okay, thank you. Any other questions?
I think molecular dynamics it has problem is that the time scale you can simulate is very short actually. Even if you
we try to compute the microsecond. Yeah, that takes long. So far, I mean, what we can do is from femtosecond to nanosecond.
yeah, if you want to
Well, ideally, we want to compute the microsecond.
yes,
Yeah, that's another 10 to 6. Yeah.
if you want to study a change that is slow in time, for example, it takes 1 second or even longer. It's still hard for you to observe it in a molecular dynamic data.
I know it's harder, but our algorithm make it easier than any other algorithm.
Oh, okay.
Okay, that I can firmly say. Okay,
And
this is really the best numerical method for modeling. I see. Much better than PPP and PME. Those are the state of art introduced in the 90s, but this is certainly much better in terms of scalability.
And I
showed you the scalability. I mean, if you have 10,000 CPUs, PPM parallelization is like 20% efficiency. Ours is almost 100. For with 10,000 CPUs.
I still have a question. You can simulate 10 million atoms or particles now, and have you considered starting, for example, you try to recover some microscopic observables with dynamics, molecular dynamics, because molecular dynamics is conducted in a smaller scale, and you try to discover some observables in a larger time scale.
How large? nanosecond we can do it, right? I mean, if we have more computer resource, we should be able to push to another 10 to 3. Yeah, I mean, 1,000 is good enough. Microsecond will maybe still not yet there.
Thank you, Professor Jinsh. The next talk will be start at 3:30, so we can rest a few minutes.
Thank you.